Let's now dive into today's topic, which is the internal AEC using SimScale. We'll particularly focus on the thermal comfort study of a classroom. In the agenda, what we have here is an introduction to the thermal comfort indices and a demo case description where we'll talk about what we are going to simulate in today's session. And then I'll jump on to the SimScale platform to show a live demonstration on how we can set up these kind of analysis using SimScale. And finally, we'll discuss about some of the key results which are relevant to a thermal comfort study. All right, let's take a look at two of the important thermal comfort indices, the predicted mean vote, PMV, and also the predicted percentage of dissatisfied, PPD. On the left, you can see there are certain parameters which are going to affect the thermal comfort of a human or an occupant. And on the right, you can see some of the compliance standards which account for the thermal comfort of the occupants, such as ASHRAE 55 and ISO 7730. There are definite ranges within which the occupant might feel thermally comfortable and ranges where there is a discomfort for the occupants. To know more about thermal comfort parameters, you can take a look at our documentation under simscale.com/documentation. Now that we know the thermal comfort indices for the study, we can move on to the simulation. The actual case study is case study that we performed with our customer Ramboll UK on Queensferry High School. So what you're looking at the right is a particular classroom that we considered for the thermal comfort study. A bit of background on what we're going to simulate again is a particular classroom from this high school where we would like to see whether the thermal comfort is within the compliance of ASHRAE 55. Which is based on PMV and PPD, as we have seen in the previous slides. Now that we know what you're going to simulate, it's good to actually define the problem statements for a CFD simulation, where we define actually what you're going to expect from a CFD simulation or the solution. So for this particular thermal comfort study, we have three major questions to be answered. The first one being, does this classroom comply with the thermal comfort criteria? And by thermal comfort criteria, we have two important parameters to check for, which is the temperature. So the next question will be, is the temperature maintained between 25 degrees Celsius and 27 degrees Celsius? And also if the airspeed is within the compliance range of 0 to 0.2 meter per second. Once when the problem is defined, the starting point of a simulation is to import the 3D model, which is the CAD geometry, which we will be using for the simulation. To start a simulation within SimScale, we would need to import the 3D model. So this can be designed with any of your CAD tools that you use in your current workflow. The important aspect of modeling a 3D CAD for simulation is that we need to have particular details that we require to set up the boundary conditions or the physics of the simulation. So on the left, you can see human models, furnitures, inlets, outlets, and some of the radiant panels. So the key aspect is that you need to actually have them as a face or a volume in your 3D model. Once when this 3D model is imported into SimScale, you can start setting up the simulation. So up next, I'll be moving on to the platform to show you how we can set up these particular analysis with SimScale and also how to extract some of the important results within SimScale. As you know, SimScale is a completely web-based simulation tool. So you're looking at the browser where I have opened the post-processing scene. What you're looking at here is a temperature distribution on the surfaces of this particular classroom. So let's imagine if you want to check the temperature at two different locations of your classroom. Let's say if you want to see the temperature of this particular occupant and also compare that with the temperature of this particular occupant at the other corner of the room. You can simply inspect any point inside the classroom to see the temperature. Let's say this particular occupant has 31.5 degrees Celsius, whereas the occupant on the other side of the room has 25.45 degrees Celsius. There's a huge difference between the temperature between the occupants here, which can be actually extracted from the result analysis. In addition to this, you can actually see the velocity distribution at a particular location, just like this. We have created a cutting plane under the diffuser to see how the diffuser inlets are acting with the temperature or the velocity distribution of the room. So as you can see, near the inlet, the temperature distribution has a high velocity, which means there is a rough draft just beneath the diffusers. So this might affect the thermal comfort of this particular occupant who are seated right below the diffuser inlets. And in case if you want to see how the air or the velocity of the air behaves in a particular region, you can switch on the particle trace. As you can see here, which shows actually the trace of the velocity of air right beneath the diffuser. You can even animate that to see how the air moves. So as you can see, there is a rough draft of air which is moving through the occupants seated here. Now that we have seen some of the results within SimScale, let's take a look at this setup and what we need to actually run this kind of simulations. So on the left, you can see on the top is the geometries. So here is where you can import the geometry for analysis. You can drag and drop geometries from SolidWorks directly. We do support SolidWorks, Autodesk Inventor, assemblies also, and also some of the general formats like STEP, Parasolid, and STL, etc. Once when the geometry is imported, you can click on them to take a look at that on the viewer. And if you're okay with the geometry that is imported, then we can go ahead and create the simulation. For this particular type, we would need to consider the heat transfer, so we'll go for convective heat transfer. And by pressing the create simulation, you can see a list of simulation parameters shown on the left, which is called the simulation tree. Here is where you actually set the conditions and also the physics of the simulation. So you can see the red circles where we need to actually address them before starting the simulation. For example, you would need to set the materials. So you can pick a material from the default library or use your custom material and select the volume which is going to act as the material selected. And next you would have to set the boundary conditions, which defines the physics of this simulation, which includes inlet, outlet, and also the heat sources that you want to set up. For the demo, I'll take a look at the already prepared setup where we actually have the inlets at these particular faces, which is going to act as a diffuser inlet, and we have a particular fixed value for the inlet. In case if you have a flow rate, you can select the flow rate and give the flow rate here as the inlet, or otherwise you can go ahead with the fixed value. And the outlets are selected similarly. And to set the heat generating sources, you can set a wall condition and give a fixed value temperature to it. In case if you know the turbulent heat flux of the particular phase that you're going to simulate, you can give the turbulent heat flux and give the value here. Once when all these boundary conditions are set, you're almost done with the setup. So you can go ahead and actually start the simulation. Getting back to the simulation, when you start the simulation, you will get an estimation of the time, the runtime, and also the computational resources that is going to be used for the simulation. You can simply press start, and this will start a simulation in our server. Once when the simulation is started, you can go ahead and modify the boundary conditions and start a new simulation again, since we actually support parallel simulations. So let's say if you want to change the inlet velocity to -3, you can simply save it and start another simulation as run 4. So you can start as many simulations as you want based upon the design criteria that you are referring to. And in case if you have any questions setting up the simulation, then you can simply use our chat function where you can chat with one of our experts and ask your questions, where we can try to actually help with your simulation setup and also guide you through this simulation setting process. Now that we have seen most of the key aspects of setting up a simulation within SimScale, I will quickly jump back to the slide to share some key results. So as an example, what we have here on this slide is the velocity distribution at two particular locations. So you can also see what's going to happen right beneath the diffuser, as we mentioned in the post-processing scene. And you can put a horizontal cutting plane at the human sitting level on this thing, as you can see on the right. So you can plot the distribution of velocity and temperature. So defining, based upon the problem statements, you can actually take a look at this velocity magnitude to see whether we are within the range of velocity 0 to 0.2, which in this case is pretty much satisfied, since we have this blue color or light blue color, which corresponds to 0 to 0.2 meter per second, except for the places or the region right beneath the diffuser inlets. And here's the same cutting plane with the temperature distributed. Here also you can see that most of the temperature ranges are within the standards, so which is between 25 and 27 degrees Celsius. Up next, you can also see the PMV index for this particular simulation, where you can see this is plotted with green being the neutral or the thermally comfortable region of this particular scale. Also, you can see the PPD value. So here everything is blue in color, which means that the PPD is well below 20% for most of the region inside the classroom. This again complies with the standards that we are comparing to. So this way you can actually get insights from the simulation and also make design changes if you have a particular region which is not under the compliance standard. That is all for today. Thank you.